Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 students. I'm Alan, and I'll be teaching you chemistry. So today we are still on topic 3, which is the periodic table, and unit 8 about trends of chemical properties of group 13 or group 3 elements and their compounds. So that is what we shall be looking at. We shall take some more time and exhaust that topic 8. But before we proceed very deeply into today's lesson, let's first check through the periodic table and remind ourselves what was covered in the previous lessons. So on the chemistry of the periodic table, you looked at group 1 and group 2, and before those groups, you had already looked at the variations in the trends of the physical properties across the whole periodic table. So today we are only adding on the group 1 and 2, and so we shall be looking deeply on the group 3. I want to emphasize a few things in here. We shall be using these names synonymously, saying group 13 or group 3A, and I need to explain what they imply. Let's take a look at this group 13 or group 3A. What does 13 imply and what does 3A imply? I'm pretty sure it was highlighted briefly in your previous lessons, but let's make a quick recap on that. So when you start from group 1 to the groups are the columns as they go downwards. So from column 1, 2, 3, going up to 13, that's where we have the boron, aluminium, and so on. So it is in group 13 because of being in column 13 within the 18 columns of the periodic table. We can also say it is in group 3A. I want you to notice A. We also have B. I will talk about it later. So in group 3A, because of the 3 electrons in the outermost shell from which they use in the chemical reaction. Even 3B, but B is actually applying to the D block elements. Whereas A, it's about the S and P elements. Then B, it's for D group, the block D elements, mostly called transition elements. So that is where we have the name group 13 or group 3A. So with that highlighted, let's look at today's lesson, which is lesson 1 on our topic, on our unit 8, which is about trends in group 13 elements and the brief study about the chemistry of boron. That is what we are going to dwell much in today's lesson. And when we talk of group 13 or group 3 elements, we are majorly looking at boron, aluminium, gallium, indium, and thorium, as you can see from top to bottom. So by the end of this lesson, our objectives are learners should be able to, 1, describe and explain trends in atomic radius and the first ionization energy, which we abbreviate as IE, of group 3A elements. That's the first objective. The second objective is you should be able to compare and explain with illustrations the melting and the boiling points of boron and aluminium. Then the third objective is about bonding in boron and its compound, where you are to fully describe the bonding in those components. So those are three objectives we are to try and achieve by the end of the lesson. And let's directly go to what is exactly in group 13 or group 3A. When we talk of group 3A, sometimes it is called the boron family, simply because boron is the first element on top, so normally called boron family. Then, as I had already said, being in group 3, they have 3 electrons in their outermost shell, what we normally call, they have 3 valence electrons. From the electronic configuration, which you already looked at, but we shall still check it out, it is in NS2, NP1, N implying the shell. Can be shell 2 or 3, 4 upwards, depending on the number of electrons an atom or the element is having. And one other aspect we need to look at before we go to the general trend is we have boron as a metallide, whereas the rest are metals. Metallide, it has both metallic and non-metallic properties. In other words, it is in between there. It is not completely metal and not completely non-metal. That's why we call them metallides. Then gallium, on the other hand, exists as a liquid, unlike other members, which are solids. And one unique factor is aluminum is the most abundant metal in the Earth's crust. It is actually made up of, it makes 80% of the Earth's dry weight, or what we can call the Earth's crust. So those are the minor facts we can talk about the group 3. Let's go to the general trends, which makes up our first objective. Take a close look at the atomic radius. We have it in a graphic form, electronegativity, and ionization energy. You have a minute to quickly look at those curves. And of course, we can't explain these trends without the electronic configuration as it is given to us. So let's quickly look at what we have in atomic radius. Remember, we're looking at the general trends in here, then explaining them. And much of these, the definitions for these terms, you looked at them prior in the other lessons. So let's look at how atomic radius actually varies within group 3A. If you look closely, we're having atomic radius on the y-axis and the element on the x-axis. You see boron has about 0.8 and thorium has 1.55. So you notice that generally, I quote that word, the atomic radius increases down the group from boron to thorium. But we have abnormal behaviors as exhibited by gallium. You notice aluminum and gallium, they have actually similar atomic sizes. We need to understand why. Before we even come to explaining why, let's look at ionization energy. I want to compare these two because they go hand in hand. If you look at the first ionization energy, which is ideally the amount of energy required to remove the first electron from a gaseous atom, or to remove the electron from a gaseous atom, is what we call as ionization energy, abbreviated as IE. You notice that we have boron with 801 kilojoule per mole. Then we have thorium as with 589 kilojoules per mole. Let's leave the variations in between and we first make a general description. So you notice that generally, the first ionization energy of the group 3 elements decrease down the group from boron to thallium. That's the general description. Now, let's look at these abnormalities. When you look closely on the ionization graph, you notice that gallium again has a relatively higher fast ionization energy compared to aluminium, and thallium has a higher ionization energy compared to indium. So those are the variations that are occurring, which we need to fully explain. Now, let's make a quick, as I told you, we have to combine them. When we're talking of ionization energy here, the factors that affect ionization energy, we look at the atomic size, we look at the nuclear charge, and the screening effect, or what we call the shielding effect, of which the nuclear charge and the screening effect work hand in hand to affect even the atomic size. That's why I want us to combine these two graphs. Again, as I told you, we can't really explain these variations minus the electronic configuration. So let's start on atomic radius. Why is, I pose a question, gallium having a similar atomic size as aluminium, and yet we expect the size to be increasing due to the extra full-filled shells that are added from one atom on top, one element on top, to another? What do I mean? If you look at the number of the proton number or the number of electrons, aluminium has 13, gallium has 31, indicating we have an addition of 18 electrons added in here. Boron has 5, aluminium has 13. We have an addition of 8 electrons. As you go downwards, more shells are being added as a result of more electrons being added. So that, of course, brings in the screening effect, as I highlighted about it, and, of course, brings in an effect on the radius. Question, why is gallium having a similar atomic size? Simple. It's due to the presence of d orbital in gallium. So what you need to know is the screening effect changes, or the magnitude of the electron repulsion changes when we bring in the d, f orbitals, as you look at the electronic configuration. Aluminium has only s and p orbitals, whereas gallium has s, p, d. We also have the d orbital in its electronic configuration. So the reason why gallium has a similar size as aluminium is simply because of the poor screening effect brought in by the d orbital in gallium, meaning that the outer electrons, the 4s and 4p, are strongly attracted by the nuclear charge. So that makes the atomic size to reduce because of the high attraction exerted from the nucleus onto the outer electrons. So in that case, makes gallium to have a relatively similar atomic size as aluminium. The same applies to ionization energy. With higher nuclear charge, that indicates it requires excessively high amount of energy to remove the electron in the gaseous atom, and that is the fast ionization energy, or the IE, as we're looking at it. So due to the poor screening effect of the d orbital brings about that change. The same applies to thallium in regard to indium. So that is what we can basically talk in terms of the general trend. And as you can see, we said boron is a metallide, so it will exhibit a higher electronegativity, which is the tendency to pull, compared to the rest of the metals, which have more electropositivity tendencies. That's why there is that sharp decline in the electronegativity. So putting the general trends on aside, let's look at the chemistry of boron and aluminium. Those are the two elements we shall base on deeply in this group. So the emphasis is on the melting and boiling points. Surprisingly, aluminium is a metal, boron is a metallide, and as you understand from your simple chemistry, metals, as they have relatively higher melting points than non-metals or than metallides, as we expect. But this is unique for boron because of its bonding. I will quickly give you an outline of the bonding in aluminium metal. It just has 3 delocalized electrons, which are attracted by the positively charged cation in the aluminium lattice structure, as you look at this one. So boron, on the other hand, exists as a giant molecule, which gives its ability to exhibit high melting and boiling point. So what do we mean by the giant molecule, and how does it come about? Let's look at the bonding in boron atoms. Unlike other nonmetals, which most of them exist as simple molecules or simple atoms, like for the group 18, boron exists as isocahedral. It has isocahedral structure, which basically implies it has many atoms with a shape of 20 sides. So this is a giant covalent molecule of boron. It has 12 atoms bonded together. So boron uses all the 5 electrons in its atom to bond with other boron atoms. As you can see, let's start with this one. It has this, is bonded to this boron. It's bonded to this boron. These are 2. It's bonded to this, which are 3. It's bonded to this, which are 4, and bonded to this, which are 5. It has 5 other boron atoms it's bonded with. So each boron uses 5 electrons, and in so doing, it creates a structure which is so rigid. It has an octahedral structure. So in that way, breaking the bonds to separate the atoms aside and separate the molecules aside becomes so hard because of its packing. This is the cubic closed packing as it exists. If you look at it from a rotated angle, but this is the structure of boron in its solid form. So this makes it exhibit great strength within its molecule or within its molecules. So breaking them at the melting point becomes difficult, requiring high energy. That is about the melting and the boiling point. So we go to chemistry of boron. When we talk of the chemistry of boron, as we said, due to its bonding, it's hard. It's actually one of the hardest in the group. And due to all the electrons being involved in the chemical bonding, they are not available to conduct electricity. It is actually a poor conductor of electricity. One other thing you need to notice, it is very, very hard to prepare boron in the lab. So much of the time, that's why originally its chemistry was not considered much, but it's being brought in and being used. So its main source is borax, as we are going to look at it briefly, and it is inert. Much of the time, it doesn't react with the acids. So it is relatively inert because of its bonding. So one aspect I need to bring in here is as a group 3 element, it uses 3 electrons in the chemical bonding, with exception when it uses all the 5. But mainly it uses the 3 electrons, and so it has the capacity to form 3 single bonds. An example is boron trifluoride. And one aspect I need to say in here, it also bonds with the mostly highly electronegative atoms, the ones which can actually share electrons with it. Then it also has the capacity to form triple bonds, as we're going to see in boron nitride, for instance. So it has the capacity to form the triple bonds. But when it forms triple bonds, that indicates the 3 outer electrons have been shared between boron and boron, for instance. So to complete the octet structure, it requires other electrons. What do I mean by the octet? Octet is just the word, it means 8. So when we talk of the octet structure, we mean the atom should be surrounded by 8 electrons. As you can see, when they are shared, so it has, if I use this example of that boron, it has 1, 2, 3, 4, 5, 6, 7, 8. The same, it has 1, 2, 3, 4, 5, 6, 7, 8. I'll talk about this later on. So when we talk about octet, after it has combined to form 3 bonds within boron and boron, to complete an octet structure, it requires extra more 2 electrons. These normally come from the other atoms it is bonding with, and that is what we call coordinate bonding. So the point to note in here is the presence of 3 electrons in the outermost shell gives boron the capacity to form 3 single bonds or 3 triple bonds with allowance of accepting other more electrons under coordinate bonding to form compounds. So one aspect that comes with boron is it forms, it has abnormal bonding features. What do we mean by the word abnormal? Because it requires those extra other electrons to form a complete octet, it tends to bond and create things which are ideally would not have happened. That's what we call abnormal. Let's look at this structure of diboron. As we said, boron has 3 electrons in the outermost shell, so it will bond with hydrogen. Each hydrogen has 1 electron, so indicating we expect a single bond between hydrogen and boron. Single bond, hydrogen and boron. Single bond, hydrogen and boron. So what does this add up to? 2, 4, 6. It adds up to 6 electrons. With 6 electrons on surrounding boron, it is not completing the octet, or it's not having 8 electrons. In simple, some of the orbital are not occupied, like as you see this empty orbital. So to counteract it, it requires other more electrons. That's why we said much of its compounds are electron deficient. When you use the simple pairing up of the electrons in the outermost shell, it leaves it with electron deficiency. So to counteract that deficiency, it borrows other electrons. I'm actually using that word in quotes, borrowing. It's not ideally the best chemical term in here. Let's see how the borrowing happens. Another boron with the similar makeup like the first comes, but in this case, what happens, these 2 electrons that were making up the hydrogen-boron bond will be involved in what we call hybridization, the coming together of orbitals. So in this case, this part will be hybridized with this orbital of boron. The same happens on this case, and it creates this kind of hybrid bond, whereby we have 2 electrons, but they are shared by 3 atoms. This is terribly not even supposed to be. That's why it is abnormal. 3 atoms sharing 2 electrons. 3 atoms sharing 2 electrons. But at the end point, boron is now exhibiting an octet structure with 1, 2 in this bond, 1, 2 in this bond, 2 in this bond and 2 in this bond, which makes it up 8 electrons surrounding boron, 2 electrons surrounding hydrogen, in this case it is stable, and also 8 electrons surrounding this boron. It is a stable molecule, true, but it is formed in abnormal way. As we shall see its use also, it is actually existing. So then we look briefly at borax. But before we look at that structure, you need to note that most of the compounds of boron are predominantly covalent, but some are exceptional, still on the abnormal bonding. We have borax, which is ionic, and exists as a giant hydrated crystal, but it can be grounded to form these small crystals. This is the borax. So as we come to the end, we look at the uses of most of the compounds of boron. Yeah, true, it has abnormal bonding, but some of its compounds are useful. For instance, the borax, as I talked about it, it's useful in pottery and ceramics. You see some of the examples made from the borax. The orthoboric acid used in making the LDC flat screens, as you see, the one you use. And the dibrane, which we talked to have the abnormal bonding, is also used as the same conductor. It is used in manufacturing the semiconductor components as you look at them. So that is what we can go through in today's lesson. I will just simply leave you with the exercise. That is the exercise 1. We have the table of the fast ionization energies and electronegativity values. We are to state and explain factors that affect the fast ionization energy. Then we are to explain why gallium exhibits a higher fast ionization energy than aluminium. And so make sure you go through that exercise as you refer back to the previous knowledge about the variations in physical properties. Thank you for your attention. Please follow the Ministry of Health regulations and stay safe. I want to see you in the next lesson. Bye.